So let's finish this part. We'll look at the assignment slide and then go into actually part 2 a little bit of today. So we'll see. But right off the bat, I want to talk just briefly about the 2 types of compounds. So if I throw out the word compound, what do you think of? 2 or more elements, exactly, combined. What's an example of a compound?
Water, for example.
Water, for example, exactly. You guys are right on track. And sometimes for this slide, and I know you guys don't have it right now as earlier, but not the slide, but the figure, I will actually branch off 2 types of compounds, and I will write molecular compound, molecular CPD for compound, and I will write ionic compound. Okay, I just want to, we'll be talking more about those. But what those have in common is what you guys said. They both have atoms that are connected together. You do a chemical formula to represent what atoms are joined together in that repeating unit. But there's a slight difference. Not necessarily that slight.
By molecular, is that the same as covalent?
Yes, molecular compounds and covalent compounds is similar. They're synonyms.
Okay.
Yes. Yep. So molecular or covalent compounds versus ionic compounds. Okay, and we're going to be hitting this later, but I kind of want to introduce you to the idea. Of course, we probably call it water a molecule, the repeating unit of water a molecule. But I don't know if you knew that actually, what's the formula for table salt?
NaCl.
NaCl. If you have NaCl, okay, that is an example of an ionic compound, ionic CPD, and you would call that repeating unit a formula unit. Okay, and I'm going to go ahead and contrast that water, H2O, actually that is a molecular compound or covalent compound, molecular CPD, and we would call that a molecule. Okay, so if you, yeah. Okay, and again, I'm not going to expect you guys to know the nitty-gritty of those 2. I do want to talk just a little bit more about this idea. So these are all examples of molecular compounds. We said water. You can see water here. And anybody know what those 2 dot dots are? 2 sets of dot dots? What?
Those are already like filled bonds.
They are filled orbitals with electrons. So basically they are where a pair of electrons here, a pair of electrons here. They're almost like little antennas. Okay, so they're just kind of spare electrons that help give that oxygen the number of electrons that it wants. We'll be talking more about that. But anyway, my point is that this molecule, any of these molecules, you could take your hand and go all the way around them. They are unique individuals. They might be connected to something else intermolecular bond-wise, but assuming you could break that bond. Contrast that with, and I know I'm skipping a few slides, my video's not working. So this is actually what sodium chloride would look like. You can't take your, over here, this is the alternating NaCl, NaCl, NaCl. And maybe some of you remember, and if you don't, we'll get there, but actually an electron is transferred. Okay, we'll talk more about that later. And so the Na, which is a metal, wants to give up its electron, and the chlorine takes in an electron. So you have a positively charged Na and a negatively charged Cl, and they stick together. And they make this cluster called a crystalline lattice structure. So you really can't draw your hands around a specific thing. You could, like, and I think it's 6. I think it connects to 6 other things. Like I could pick, I won't get 6, but I could go this way, I could go this way, I could go this way. The small ones are the NAs, and the big ones are the CLs. Okay, so I could go any which way. That's what I mean, you know. Okay, so then just to follow that up, when we're dealing with molecular compounds like water, each little unit is by itself. It's its own little entity, its own little family. Okay, when we're dealing with something like NaCl, in its solid state, it's an alternating little community of actually ions that you can't designate which is with which. Okay, so another thing I want to kind of quickly introduce you to is this idea of the physical phases of matter. And we're throwing out plasma for now. We're just dealing with solid, liquids, and gases. Okay, so I like this, this little picture of an ice cube. Of course, ice itself is solid. And the things that solids all have going for them is they are, let's see, I think, yep. Does anybody see a problem with this? Actually, on your slide, if you want to mark out where it says liquid and put solid, you could. And where it says solid, put liquid. Didn't catch that in my office. Again this semester. So starting with a solid, this is what a solid looks like. Okay, it's got a lot of, can you see those, I call them dot, dot, dots. You see all those, these little connector mark thingies? Okay, those are actually what we call intermolecular bonds. They are intermolecular bonds. And if something's in its solid state, it has lots of them. Okay, something, and it's not shown down here, there are also intermolecular bonds here. When water is in its liquid stage, they're just fewer. And when water is in its gaseous state, basically there's no, what we call no IM for intermolecular bonds. Okay, so that's kind of what we got going on there. Of course, if how would I go from, what do I have to do to get an ice cube to liquefy? Change the temperature, yeah. Heat it up, zap it with a little bit of heat. Okay, and when you zap it with a little bit of heat, what you're doing is breaking these, some of them, intermolecular bonds. Then what do you have to do to get a liquid to go in its gaseous phase? Heat it up some more, boil it, heat it up some more, exactly. And so that's when basically you get it to break all of its intermolecular bonds. So here's a table looking at the three physical phases, solid, liquid, and gas. And I bet you guys would buy this. If I were to ask you, for instance, a solid, assuming you're not going to liquefy it, it's going to keep its size and its shape. If we contrast that to a gas, gases have no intermolecular bonds, and basically they're going to, whatever container you put them in, they're going to take on the shape and the volume of their container. So, and liquids are, will take on the shape but not the volume of their container. Wait, yeah, the definite size. Over here, we kind of talked about intermolecular bonding. The solids have a lot of intermolecular bonding. So up at the top, I could put IM bonding. That's what I kind of referred to a minute ago. We have high degree of bonding for solid. Basically no bonding if the gas is behaving ideally for gases. Now I think this is kind of neat. You guys know that all matter has motion. I just think that's so cool. Okay, so if something is in its gaseous state, it has the most amount of motion. Okay, if something, a high amount of that motion is kinetic energy. Something that's a solid state, it still has motion, but not as much. Okay. So those dot, dot, dots I showed you a minute ago, those are the intermolecular forces that actually are broken as we melt water. They're broken as we evaporate water, have it go from a liquid to a gas. Okay. And they're formed as we go back the other direction. Those intermolecular bonds are formed. So it almost seems like it could be a rap show. So if we go S for solid, L for liquid, G for gas, okay, as I'm going from left to right, am I breaking bonds or forming bonds? Breaking. I am breaking bonds. And you guys told me I need to add heat, right? Okay, good. I'll just put E for energy. So now, if I go back the other direction, if I go from a gas to a liquid, what do we call that?
Condensing.
Condensing. Yep, going from a gas to a liquid. How about if I go from a liquid to a solid?
Sublimating.
If I go from a solid to a gas, I'm sublimating if I skip the liquid stage. But what if I go from a liquid to a solid? Think of your ice cubes.
Freezing.
Yep, freezing. You got it. Freezing, and this is condensing. Okay, so are bonds being broken or bonds being formed? Formed, exactly. And what this little thing will tell you, or what this statement says, is bonds are formed, energy is released. So here, bonds formed, and then E released. That is such a big player in our atmospheric weather, day-to-day weather. But anyway, okay. All right. So I've got a couple of, I need to talk about properties. Property is a characteristic. I tell people, like, if you're playing the I'm thinking of game, okay, what you do is the person who thought of it kind of goes back and forth with the person who's guessing it with properties about that object, the object in question. What are the properties, okay? So we can kind of break them up into different kind of properties. It's important in science to be able to identify things. You know, black canvas bag, okay? What temperature does it burn at, okay? How much does it weigh? Okay, those are all properties of this bag. I don't know if it's canvas or anything, but
I don't know.
okay. So those are properties. Now, we have broadly stating something called physical and chemical properties. Just looking at something, that would be an example of a physical property. Now, to get to the crux of a chemical property, you need to do some sort of chemical reaction. Okay? So to assess a property that's a chemical property, again, you need to do some sort of chemical reaction. And the hint for, well, I don't know if I did a chemical reaction. Okay, the hint for a chemical reaction is, were new substances formed? So I'll put question mark chemical reaction, question mark, and I'm going to say, are new substances formed? And if the answer is yes, then it was a chemical reaction you performed to assess that particular property. All right, so here we go. Some are more obvious than others. This whole list are properties or characteristics of objects or matter. They are characteristics that are physical. No chemical reaction needs to occur. What's the color of an object? Well, that can be important, you know, like the black. What is the state? Is it a solid, liquid, or gas? That's a characteristic. It's a physical characteristic, physical property. The next two kind of throw people off sometimes. At what temperature will that material change its physical phase, its state, okay? So what do you think? Water, which one freezes at a lower temperature, water or alcohol? Lower temperature. Alcohol, yep. Yep, so alcohol freezes at a lower temperature. So honestly, if you had two clear liquids, that would be a cool little test you could do. You know, put them out when it's like -5, okay, Celsius, and see which one doesn't freeze. Now, I'm not sure what the freezing point temperature of alcohol is, because it depends on what kind of alcohol it is. But sometimes we see it looks like you have new substance, but you don't. You still have your water molecules and your alcohol molecules. Okay. Density, we'll talk more about density. That's kind of how crammed the material is in a volume. Does it dissolve? Well, I don't know. But if it dissolves, it could be a clue to what that stuff is, to you figuring out your 20 questions. Okay. So those are all. I like viscosity too. Viscosity is like how thick something is. Okay, so you could have, again, two clear liquids, and one of them could be water, and one of them could be Karo syrup. And somebody holds and dumps them out for you. You're like, oh, I know what that is, because you showed me the viscosity. So those are all physical properties. This is showing you a physical property of melting. On the left and right, you see these two white powders. You're like, I don't know which is which. Okay, one will kill me, no, and one will clear my headache. I'm not sure if naphthalene will kill you if you ingest it. I don't recommend it. It's like the mothballs, you know. Yeah. But we know that underneath it are the captions at the temperature that naphthalene melts at 80.2, okay, and aspirin melts at 135. So if it's in boiling water, what temperature are those two test tubes seeing? Celsius temperature, yeah, 100 degrees Celsius. Does that make sense? Okay, so quick and dirty, you're like, the one that melts must be the naphthalene. Don't eat it. Cool. So these might be things that you'd run into. I think your homework is actually, I'm going to kind of show you a screenshot of your homework, and I'm going to push the homework out there, send it as an email. But these are questions you need to be able to kind of answer, like the color of something's a physical property. The next one, when iron is transformed into rust, why is that a, did I say chemical? The color of something's a physical property. Why is when iron's transformed into rust, why is that a chemical property?
Because rust is a different substance.
Rust is a different substance than iron itself, yep. Rust is iron oxide types. Why is the fact that dynamite can explode, what sort of chemical reaction are we doing there?
Combustion.
Combustion, yeah. Yeah, you're like, you use it up, it's all spent. Okay, but not everything will explode, but it's a property of dynamite. Density is a physical property. The temperature at which something melts is always physical, and again, color is physical. Okay, so we have chemical or physical properties. We have another set, kind of a yin and yang properties. They're intensive and extensive properties. Now, I always still remember this. I always start with the intensive, and I think independent. So I'll kind of tell you what I mean. So for intensive, if you put independent of amount, they match up. Independent of AMT for amount. So an example of that is color is a good example of that. Like if I were to go to the store and I'd have this bag there, and actually it was hanging with 5 other bags. It's a nice bag, I think, Christian. So all 5 of those bags, they're black. Okay, so color is independent of amount. Okay, what's another example? Well, okay. Extensive depends on amount. So, depends on amount. Now, if we stick with the whole, can't spell, AMT for amount. If we stick with the whole bag thing, okay, property we can go with is mass. What's its mass? What's the mass of that object? Well, it does depend upon amount. Am I talking about the mass of one bag, or am I talking about the mass of a box of bags as they come in, okay? So an example, something that does depend upon amount would be mass. So that's an example of that. So I said mass for extensive and color for independent. With my writing now, you see why I go with PowerPoint slides. Okay, cool. So this is kind of a subtle, we talked about physical and chemical properties. Physical and chemical changes go hand in hand with that. Okay, so if you're going to melt something, is that an example of a physical change or a chemical change? How many people think physical change if you're melting it? Me too. Yeah, very good. Cool. So some of these are trickier than others. They're kind of like little, in your homework, when you go to do this and for saying whether a chemical reaction has occurred, just do your best. Some of them are harder than others. For instance, like if your shirt gets changed colors, because of bleach, I usually say, well, can I undo that process? Well, I can go out and get a Ritz dye and try to get it back to the right color, okay? But I don't think you can undo. I think something kind of permanently has been done, so that's why it's a chemical change. The next one, water condensing, okay? Basically water vapor, when it reaches cold air, goes ahead and starts coming out its vapor phase and liquefying. So that is an example of physical change. The whole plants making carbon dioxide during photosynthesis, or using carbon dioxide to make sugar during photosynthesis, that's a chemical change. And when the last one's a physical change because it's a phase change. Okay, so let's take a look at these. Now, a few things while I'm thinking of it. I said that there is a companion course out there for online, okay? If you're in HawkNet, if you click online, you can get to this course companion site. There is a tab that says doc sharing, and I think I might have mentioned this the other day. Okay, so doc sharing, I want to see, no, I can't break it up because I'm not on the internet. But I have the answers to the odd problems, okay? So the answers to the odd problems. That's the point I was trying to get to. So doc sharing, A and S for answers to odd problems. I don't know why Petrucci did this in this edition. In the previous edition, like most textbooks, he had it in the back of the textbook. It's not in the back of the textbook for some dumb reason. So I'm going to pull these up and we'll take a look at them. Sometimes I do that. If I can find them. Okay, so this is what you're looking at. Now, you don't have to answer using complete sentences, but you do want to answer them with complete thoughts. Okay, so the first one is, state whether these properties state whether the following properties of matter are physical or chemical properties of the matter. So some of them are harder than others. So let's do the first one. An iron nail is attracted to a magnet. So picture your iron nail, picture your magnet, they're coming together. Is any new substances formed? How many people think yes? How many people think no? I agree. So how many people think it's a chemical change? How many people think it's a physical change? Yeah, me too. Or property. So you'll do great. And then the second page looks like this. Well, it's not the second page, but there's 6 questions, and these are the other 6. Okay? It'll be fun.
How are we turning this in?
Yeah, so what'll happen then is just turn it in Monday. It'll be due Monday at the start of the period.
Just like a piece of paper then?
Mm-hmm. Yep, piece of paper.
So type it out or?
Nope. Just make it out, yeah. Yeah. Yep, that should be good. And you don't have to restate the question, so.
Do you have a printout of these? Because I might have seen that look back.
Yeah, that's what I was kind of thinking. I will send, if I send an email, will you get it?
Yeah, that'd be perfect.
Okay, I will send an email. That's easy.
I'm keeping mine until I get mine. If I can, as long as I get it.
So let's